Metglas is a thin amorphous metal alloy ribbon produced by using rapid solidification process of approximately 1 million degrees Celsius, 1,800,000 degree Fahrenheit 1 million Kelvins. This rapid solidification creates unique ferromagnetic properties that allows the ribbon to be magnetized and demagnetized quickly and effectively with very low core losses of approximately 5 milliwatts per kilogram at 60 Hz and a maximum relative permeability of approximately 1 million. Metglas is based on technology developed at Allied Signal Research Facilities in Morristown, New Jersey and Vacuumschmelze in Hanau, Germany. The development of amorphous metals began in 1970. Over the years, many new alloys have been found using the same principles of rapid solidification. Metglas, also known as metallic glass alloys, differ from traditional metals in that they have a non-crystalline structure and possess unique physical and magnetic properties that combine high permeability, strength and hardness with flexibility and toughness. An amorphous metal transformer is a type of energy-efficient transformer found on electric grids. The magnetic core of this transformer is made with a ferromagnetic amorphous metal. The typical material, Metglas, is an alloy of iron with boron, silicon, and phosphorus in the form of thin, for example 25 micrometers, foils rapidly cooled from melt. These materials have high magnetic susceptibility, very low coercivity and high electrical resistance. The high resistance and thin foils lead to low losses by eddy currents when subjected to alternating magnetic fields. On the downside, amorphous alloys have a lower saturation induction and often a higher magnetostriction compared to conventional crystalline iron silicon electrical steel. The main application of AMTs are the grid distribution transformers rated at about 51,000 kV amperes. These transformers typically run 24 hours a day and at a low load factor, average load divided by nominal load. The no-load loss of these transformers makes up a significant part of the loss of the whole distribution net. Amorphous iron is also used in specialized electric motors that operate at high frequencies of perhaps 350 Hz or more. More efficient transformers lead to a reduction of generation requirement and, when using electric power generated from fossil fuels, less CO2 emissions. This technology has been widely adopted by large developing countries such as China and India where labor cost is low. AMT are in fact more labor-intensive than conventional distribution transformers, a reason that explains a very low adoption in the comparable, by size, European market. These two countries can potentially save 25-30 terawatt-hours electricity annually, eliminate 6 to 8 gigawatts generation investment, and reduce 20-30 million tons of CO2 emission by fully utilizing this technology. The alloys of boron, silicon, phosphorus, and other glass formers with magnetic metals, iron, cobalt, nickel, have high magnetic susceptibility, with low coercivity and high electrical resistance. Usually the electrical conductivity of a metallic glass is of the same low order of magnitude as of a molten metal just above the melting point. The high resistance leads to low losses by eddy currents when subjected to alternating magnetic fields, a property useful for example transformer magnetic cores. Their low coercivity also contributes to low loss. Amorphous metals have higher tensile yield strengths and higher elastic strain limits than polycrystalline metal alloys, but their ductilities and fatigue strengths are lower. Amorphous alloys have a variety of potentially useful properties. In particular, they tend to be stronger than crystalline alloys of similar chemical composition, and they can sustain larger reversible, elastic, deformations than crystalline alloys. Amorphous metals derive their strength directly from their non-crystalline structure, which does not have any of the defects, such as dislocations, that limit the strength of crystalline alloys. One modern amorphous metal, known as vitriol, has a tensile strength that is almost twice that of high-grade titanium. However, metallic glasses at room temperature are not ductile and tend to fail suddenly when loaded in tension, which limits the material applicability in reliability critical applications, as the impending failure is not evident. Therefore, there is considerable interest in producing metal matrix composites consisting of a metallic glass matrix containing dendritic particles or fibers of a ductile crystalline metal. Perhaps the most useful property of bulk amorphous alloys is that they are true glasses, which means that they soften and flow upon heating. This allows for easy processing, such as by injection molding, in much the same way as polymers. As a result, amorphous alloys have been commercialized for use in sports equipment, medical devices, and as cases for electronic equipment. Thin films of amorphous metals can be deposited via high-velocity oxygen fuel technique as protective coatings.